So here's lesson E, applying Newton's laws, number 3. Up to this point, we have studied the dynamics of a single object subject to forces from the environment. And as we've seen, these problems can be solved by an application of Newton's second law after all the forces have been identified. But Newton's third law tells us that real-world motion often involves two or more objects interacting with each other. We further found that forces always come in action-reaction pairs. So remember, Newton's third law states that every force occurs as one member of an action-reaction pair. The two members of the pair always act on different objects. The two members of an action-reaction pair always point in opposite directions and are equal in magnitude. So our goal now is to learn how to apply the second and third law to systems of interacting objects, such as masses attached by ropes and placed over pulleys, or objects that are placed next to one another. So Newton's third law is really what we are focused on in this lesson of interacting objects. So imagine we've got these two boxes sitting here. Box A is pressed up against box B and we're pushing on box A. As long as these two objects are attached in the same plane of motion, they're going to have the same acceleration. And we call that an acceleration constraint. Okay, so these two objects are constrained to have the same acceleration as long as they're attached. But what we can do is look at them individually and use that acceleration constraint to help us solve problems involving them. So while it's true that whenever two objects are attached in the same plane of motion, they'll have the same acceleration, we can't always assume that those two objects will have accelerations of the same sign. There are situations where we have attached objects where one object will have a positive acceleration and the other will have a negative acceleration, although the magnitude of the accelerations will be the same. For example, these blocks here are connected by a string, so they're constrained to move together and their accelerations have equal magnitudes, but A is going to have a positive acceleration to the right and B is going to have a negative acceleration in the downward y direction. But both accelerations will have the same magnitude. So let's take a look at an example. So the figure here shows a 5 kilogram block A being pushed with a 3 Newton force. In front of this block is a 10 kilogram block B, and the two blocks move together. We want to know what force does block A exert on block B. Okay, so let's start by drawing free body diagrams for each block individually and look at the forces acting on them. Block A then, of course, has a weight force in the y direction and a normal force, as does block B. I've drawn the weight force and normal force of block B longer than block A because block B is more massive than block A. So now let's look in the x direction then for block A. Block A has this force from the hand pushing on block A. Block B does not experience force of the hand. The hand is pushing on block A. Okay? But what block A does experience is a force from block B back on it. Okay? So because we have this connection right here, block A pushes on block B. Newton's third law tells us that block B pushes back on block A. So then, on block B, then the only force in the x direction is going to be the force of A on B. And those two forces are the action-reaction pair between these two objects. Okay, so those two are the action-reaction pair here. So now when we go to start looking at the forces then acting on block A, the net force on block A will be equal to the force of the hand minus the force of B on A, which will be equal to the mass of block A times the acceleration. And because these two objects are connected, their accelerations are constrained to be equal in magnitude. Okay, so that's what we've got right now for block A. Let's take a look at block B. The net force then on block B in the x direction is just the force of A on B equal to the mass of B times our acceleration. Okay, so now we've got these two expressions then for the forces on each block. But we've also got another bit of information. We've got Newton's third law, which tells us that the force of B on A has got to equal in magnitude the force of A on B. So with this information, our two equations become this here. Now our goal is to find this force A on B. Okay, so what we need to do is eliminate this unknown acceleration here. From this first equation then, our acceleration can be solved to be this right here. And so what we can do is take this and substitute it into our other equation, which will give us this right here. Okay, so now we can plug in our values and begin to solve. So we can begin with this and result in this. So now the critical step in solving problems like this is to correctly identify the forces and drawing the two free body diagrams. The rest of the problem really just consists of writing the second law equations directly from the free body diagram and then using the new information of the acceleration constraint to solve for the desired quantity. And really in these interacting objects problems, there's kind of two ways to go about solving them. There's the substitution method and the elimination method, which should be familiar from your algebra classes. Okay, so now let's talk about ropes and pulleys. Let's talk about tension real quick. In a rope, all parts of the rope are connected, and no part is accelerating when we're pulling on a rope. So when this hand pulls on the rope with some force, the rope pulls back with a force equal to that. That forms an action-reaction pair. What's happening inside the rope is that each piece of the rope is pulling on the piece next to it, all down the entire rope to the wall, to the point where the wall then is pulling back on the rope just as hard as the rope is pulling on it. Because all parts of the rope are connected, no part is stationary. The tension in a stationary rope pulls equally hard at both ends of the rope on whatever object the rope is attached to. Now these ropes that we're going to be dealing with, and ropes and strings, we're going to use what's called the massless rope approximation and ideal pulleys, which means if we've got two blocks connected by a string, we can omit the string if we assume that string is massless. Then it's as if A pulls directly on B and B directly on A. So the forces of each block from the other block have the same magnitude. It's just a way to simplify problems. Okay, because tension in a massless string remains constant even as it passes over a massless, frictionless pulley. So the problems that we'll be dealing with, we'll deal with massless strings and ropes, massless and frictionless pulleys. And in many situations, we'll be interested in the force exerted on a pulley by a rope that passes through it. In those situations, even though that pulley is frictionless, the tension force still pulls on the pulley because the rope is under tension on both sides of the pulley. The pulley is subject to two tension forces, one from each side of the rope, and the net force on the pulley due to the rope is then the vector sum of these two tension forces. So let's look at an example of a pulley system. We got a 200 kilogram set used in a plate is stored in the loft above the stage. The rope holding the set passes up and over a pulley and then is tied backstage. The director tells a 100 kilogram stagehand to lower the set. When he unties the rope, the set falls and this unfortunate fellow is hoisted up into the loft. What is the stagehand's acceleration? So what this situation is, it's a kind of a different situation of what's called an Atwood's machine. Okay, we'll be doing some work in class with Atwood's machines. Okay, so to begin with this, like we'll do with any force problem, is we start with free body diagrams. And what we'll do is draw a free body diagram for each object individually. So we've got the person, which I'm going to call object 1, and we've got the set, which I'm going to call object 2. So for object 1, then we have a weight, FG1, and we have a tension. Now, this person, the person is going to accelerate upwards, so we're going to draw the tension slightly longer. On set 2, on the object 2, then we have object 2's weight, which we'll call FG2, and the tension. Now, there's no difference because we're going to assume that this is a massless and frictionless pulley. That we're going to find that the tension between the two objects is the same at both ends of the rope. So what we have to think about here is the direction of the acceleration. Both objects are going to accelerate at the same rate. They're constrained to accelerate at the same rate. Object 1, though, the person is going to accelerate upward. Okay? So what we know then is net force equals mass times acceleration. The acceleration is going to point in the same direction as the net force. So my net force is upward. And when we go to solve two object problems like this, we're going to want to set our positive direction in the same direction as the acceleration. Okay? So if we know that our acceleration is upward, we know our net force then is upward, and so we're going to set the positive direction as upward for object 1. Object 2, though, is accelerating downward. Okay, it's accelerating in the downward direction. So in this case, because our acceleration is downward, that tells us that our net force is downward, and therefore we're going to set our positive direction as downward for object 2. Okay? They're both constrained to accelerate at the same rate, but in opposite directions. And we're setting our positive direction for each object in the direction of that acceleration. Okay, so what we want to do now is we want to begin to develop an expression for each object individually and begin to solve. So if we look at object 1 individually, then we know that the net force on object 1 will equal its mass times acceleration. So what is providing that net force? We've got a tension minus the weight of object 1, which is the person. Okay? And we know also that to solve for weight, weight is mass times g. So this is mass 1. Okay? So we have here an expression for the net force that's acting on object 1. So let's do the same then for object 2. And when we do that, we end up with this right here. Okay? So what's happening here is we've got, because our acceleration is pointed in the downward direction for object 2, down is the positive direction. So we end up with a positive weight, a negative tension. These tensions are both the same. Okay? These accelerations are both the same, and what we want to solve for is that acceleration. To do that, there's two ways to do that. Like I mentioned earlier, is there's the substitution and the elimination method. And so what I'm going to do is I'm going to show you simultaneously how to solve using both methods. On the left-hand side over here, I'm going to do the elimination method. Over here, I'll do the substitution method. With elimination then, because we have these two expressions for each object, we can combine those two equations. So we have tension minus M1G equals M1A. And we've got M2G minus the tension equals M2A. Now it's because these tensions are the same and the accelerations are the same that we can use this method. Okay? So we combine those two equations, we end up with M2G minus M1G equals M1A plus M2A. Okay? These tensions subtract out. Now because G shows up on both terms on this side of the equation and A shows up on both, we can extract out the G. So we end up with G M2 minus M1 equals A M1 plus M2. Okay. And we're going to remember, this is important to recognize and realize that M2 in this case is the heavier mass. Okay. So what we can do now is we can solve then for our acceleration, and we get G M2 minus M1 over M1 plus M2. Okay, and so this then becomes our expression for our equation for our acceleration. So now let's look at the other method. Let's look at the substitution method. Using the substitution method, we're going to look at our original two equations here, and we know that our tension is the same for both sides of this pulley system. Okay. So what we're going to do is we're going to solve first for one of these tensions and then substitute that tension into the other equation. Okay? So if I have, say for example, I solve for using object 2, I solve for the tension, I get M2A minus M2G. I clean this up and it becomes M2G minus M2A. Okay, so now what I can do is I can take this tension and I substitute it into the other equation, and then I end up with this. M2G minus M2A minus M1G equals M1A. And so then I go through and what I want to do is I want to put the G's on one side of the equal sign and the A's on the other side, which gets me this right here. Notice now we're exactly the same as this method here, okay, the substitution method. So what we're doing with this, our goal here is we've got an unknown A, we've got an unknown T. We need to get rid of one of those unknowns. We can use then the elimination method to get rid of that unknown, or we can use the substitution method to get rid of that unknown. It's totally up to you which way you want to go with those. Either way is going to end up giving you this equation for the acceleration. Okay. Now, what's important though is that you know how to do that, and so you would have to be able to show that you know how to use one of these two methods to arrive at this. Okay. So when we go to take and put numbers into this, then here's what we end up with: the mass of the set minus the mass of the person over the sum of the two masses times g. We end up with an acceleration of 3.27 meters per second squared. We know this makes sense because neither of these objects, because there's this tension force up here, right? Neither of these objects are in free fall, so our acceleration has to be less than free fall acceleration of g. Okay, so there is that example, and the end of this lesson. Now there's going to be one other video attached with this unit dealing with I'm just going to put a couple of other examples on that is an optional video for you. Okay, see you in class.